Good afternoon, everyone. Yeah. Okay, my name is Locke, and I'm from the Division of Physics and Applied Physics. So it is my honor to chair and to introduce Professor Stefan Thurner in this afternoon session of the conference. Professor Thurner is currently a full professor for Science of Complex System at the Medical University of Vienna, where he had founded the Science section for Science of Complex System. He is also an external professor at the Santa Fe Institute. His research includes the study of complexity in economics, life sciences, and lately in social sciences. He had also explored into the fundamentals of complex systems through physics and applied mathematics. Professor Thurner had obtained a PhD in theoretical physics, and he had also obtained a PhD degree in economics. I believe this had played a role in the depth of his research in various aspects of complex systems. So last week, I had an opportunity to listen to Professor Thurner talk on what is systemic risk in financial market and how to eliminate it during the NTU Warwick Winter School on Complexity. So this is a wonderful talk. Professor Thurner has shown the importance of complexity thinking. First, he introduces a measurable quantity known as systemic risk to encapsulate the financial risk of the network of banks in the country. By means of this complexity concept, which involves the whole of the financial network, he moved on to show how the introduction of a systemic risk transaction tax can self-organize the financial system into a structure with drastically reduced systemic risk, which is essential to avoid financial collapse. I find this to be a very important piece of work because it is a clear instance of how complexity science can contribute concretely to the solution of societal problems, which in this case concerns the economy. This is not the only piece of work which shows Professor Thurner's uncanny ability to exploit understanding of the complex whole to manage the parts of the whole. I urge you to read up also on his proposal of a novel review system of scientific paper publication, where he again demonstrates this unique quality, where he shows how a good grasp of complexity science can positively impact our social system of scientific publication. So today, I believe Professor Thurner is going to show us another important aspect of complex system, which is the emerging patterns of scaling in nature. So without further ado, let us put our hands together to warmly welcome Professor Thurner to deliver his lecture.
Thank you very much for the introduction, and thank you, Jan, for the invitation. I'm immensely enjoying myself with the conversations I'm having at NTU and being in Singapore. Fantastic. I've observed many times that when speakers, before they start presenting their talk, that they start excusing themselves for making last changes to their title, and I'm gonna do exactly the same now. I've changed the last 3 or 4 words of my title, and I will not give you a theoretical physics lecture on very detailed descriptions of complex systems which allow you to see them in a little bit more general way. If I had only 20 minutes or 30 minutes, I would dare to bore you to death with these details. But since this is going to take an hour, I decided for the best of all of us to take and adopt the 180-degree strategy that we have learned in the previous talk, and I will talk about the opposite of theoretical physics. And what is the opposite of that? It's computer games. So why don't you see computer games in the title? I put big data here instead. You will find out why. I put in big data here because this is a term which makes the title suspicious, as we discussed yesterday, announcing something big and then not delivering during the talk. Yeah, big data is a thing that I don't understand, and I would like to start talking about that. So maybe a bad thing to talk about things you don't understand, but maybe you also don't understand. So if you talk about big data, what is big? You need a scale for saying what is big and what is small. So I think big data is big if the size of data is big compared to the amount of processing you can do with it. Maybe we can immediately start quarreling about this. But in this sense, physics always has been big data science. Copernicus had, I don't know how many almanacs of numbers, which he tried to make sense out of. His computational powers were big compared to the computational powers of other people at the time, but it was only in one brain. Same with Kepler, Newton, Planck, Neumann, etc. And then things might start changing again. So I claim that since 1532 we are doing big data science. Yeah, what science is, we try to find compact formulas to explain all of the data that we have at hand. And what's the bottleneck? It's the brain to process the data. So data is big if the data capacity or the capacity to store data or the amount of data that we have is large compared to the computing power that we have. Okay, is that big data? Maybe, yeah. So how much, let's put numbers to this equation. How much data is there in the world? Well, there is this many exabytes. I don't even know how many zeros that has, but it's a lot. And what's important is that data increases, the stored amount of data increases annually by an amount of 23%. To give you a feeling for that, so I took this from it's not my numbers, it's from this science publication. If you have a unit of 1 in 86, it's 60 units 20 years later. Okay, 2007, that's when these people take 2007 here. Yeah. So how much computation is there in the world? How much can we compute? This is the number, the size of data we have. Now we need how much computer power is there in the world. Does not matter how much computer power there is in the world. So we are beyond, if in 2007 you hooked up all the computers together, you could do a computation of one single human brain. So we are well beyond that. And no matter where we have been at 2007, we know that computing power is growing at about 60% annually. That means in a range of over 20 years, a unit of 1 becomes around 10,000 units. Okay, so what does that mean? Now we are putting in the number for the data, amount of data that we have divided by the computing power, and we find that it's getting much less than 1. So I'm claiming we're not in a big data era now. We are in the opposite. Our computer power compared to the data that we are collecting, which is impressive, but our computer power is even more impressive. So, okay, so it seems that it's not the computer power that's the bottleneck anymore, as it used to be with Kepler and those guys. It's also not the possibility for data acquisition. So what's the bottleneck? Why still can't we predict a financial crash, which is maybe ahead of us in 2 days? Why can we still not treat the flu? So 20% of Austrians are currently suffering the flu. No one can do anything about it. This year the vaccination doesn't work. We cannot foresee social unrest. We cannot predict the traffic in any city, etc. Yeah? We can also not compute maybe the most important number in the world. How many will we be in the next 20 years? So this is why we have another bottleneck. I think we have another bottleneck, and that's the complexity behind systems. Okay, so complex systems are much, much harder to understand and to compute than simple systems like physics or chemistry. Data alone will not help us, and big data is certainly necessary, but it's not the end of the story. It's not all of it. So the limiting factor is complexity. So the theme of today is, how can big data help us to understand our species, or little data? If we are running more and more into the situation that we are confronted with data sets that are complete, in a sense that there is everything to a system that you can know about the system, that you have everything in your disks, in your terabyte disks. What to do if you have all information about the system? What do you do then? You're running in this embarrassing situation that you cannot blame anyone anymore for not having the data. You have it all. It's you that's limiting the progress. Yes, and is the situation we are living in now the moment that finally we can make a hard science out of social sciences? Are we there yet? So we're not the first to do that. So many of you might know who this is, a very poor career. This is Auguste Comte, who 200 years ago said exactly the same thing. Let's make a hard science out of social science. He wanted to do what his successful friends were doing in physics and in chemistry. He wanted to do a science of society and of people. He tremendously failed. He did not become a member of the academy. He did not become a professor of the Polytechnic school. All he became was a math tutor, preparing students to enter the Polytechnic. He coined a name for the science that he envisioned. It was called socio-physics. That did not fly at all, so another piece of failure. Then he coined another term, sociology, dates back to him. That took on, but still, I think he considered himself as an absolute failure. So we are doing exactly the same thing again, running the risk of becoming a complete failure again. Is it the time, or it's the time, that social science finally becomes an experimental science? I should not say hard science, an experimental science. A science that's quantitative, and predictive, and testable. Okay, big claim again, and maybe we're gonna fail again. But critics will immediately say this is impossible. Humans have a free will. You will never make it. Interconnections between humans are way too high dimensional. You will never gonna be successful. And further on, you don't have data on a societal level. And I would like to make clear that these three things are not true anymore. Maybe the free will thing is still there, but we know that there's objects in the world which are much more unpredictable than humans, quanta or atoms, and still we can make out a lot of sense of solid-state physics, even though we know that the individual things are highly, highly unpredictable. maybe more than humans. We have to talk a little bit about what prediction means. Prediction nowadays, or in the context of complex system science, is certainly something very different from what Newton understood by prediction. So in the 18th, 17th, 18th, 19th century, a prediction was an exact prediction. It was a solution to a differential equation, and it was predictions of trajectories of states of a system. Then if you were dealing, or if you're dealing with too many particles, this concept breaks down. And we entered a crisis around 1900, and statistical physics kind of reduced the concept of prediction to a probabilistic kind of prediction. But still we had particles there, interactions, weak interactions between particles, and we could predict the behavior of the collection of atoms or molecules. In the 1920s, when quantum mechanics came about, the problem emerged that your components were not predictable anymore. They were subject to quantum mechanic laws. But still, we know that we can predict behavior and properties of the collective of atoms and molecules. And in the 1990s, finally, not only the components become unpredictable in complex systems, also the interactions become not so certain anymore. The types of interactions that people are now studying is not just the four forces of physics, but thousands and maybe more than that, types of interactions, for example, interactions that humans can engage in. Okay, this is now the state of complex systems where we have unpredictable components, complicated and maybe also unpredictable interactions. But the hope is still that the collective will be predictable. So what is a society? Society, in one sentence, is a co-evolving multiplex network. I've shown this slide last week, and I used it for a different context, but now society is a co-evolving multiplex network. You have individuals. These are the nodes in the network. Individuals have different states. These are maybe females and males. Circles are rich males, and circles could indicate any other states, being the wealth, or whatever. And you see that these nodes are connected not only by one type of network, but by different types of networks. Can be friendships, can be trade, can be hostile interactions, can be a whole collection. Whatever kind of interaction you can think of, you can draw it as a network layer in this multiplex network. What is important is that the states, neither the states nor the networks that you see here are constant in time, but they change over time. And this is where all the magic comes from. All the magic of complex systems. And what is the magic of a complex system? We have heard it today by Brian Arthur. You have states of the system which depend very much on the topology of the structure of the network. And the network depends very much on the states that the nodes are in. And especially the change of states depends on the networks, and the change of the networks depends on the states of the nodes. So I tried to put this into, so the states of the nodes we denote by sigma, and the network or the matrix of type alpha we denote by m. Okay. So here, don't be scared of this equation. All what it says is that the temporal change, the change of states in the system, is some function of how the network looks right now and how the states are looking right now. This is what physics is doing. This is what Brian Arthur called the differential equation, Newtonian kind of thinking. But if at the same time you allow your substrate where your processes are happening, your networks, if you allow those to change in time as another function which depends on the network and on the states, if you're adding such a term, then you're getting a complex system. Okay? This is physics. This is, I don't know what, but the combination is a complex system. There's one example in physics which is of this type. This is general relativity, where this would be the space, how space changes as a function of the dynamics of the system. Here's the dynamics of the system, and the space changes as a function of it. But that's maybe the only example in physics where you have such a thing. In complex systems, you almost all the time have such a structure. Okay, you have a chicken-egg problem, as Brian Arthur mentioned. You cannot fix a boundary condition anymore. So if this is a set of differential equations, you would like to fix a boundary condition, then solve it. But due to this term, you cannot fix the boundary conditions anymore. That's exactly what you have in complex systems. Yeah, if you have a set of differential equations that describe the dynamics of a system, and your boundary conditions also become dynamical in time, are also governed by a differential equation like this one, and if you couple these two, you cannot solve that system anymore. We've learned this from Newton, that this is not possible. And all you can do with these kind of systems is to run algorithms, as we have heard today. You can play with them. You can run algorithms and watch these things. You cannot solve them in the sense that we were used from Newton. Okay, so is this a useful, and does this make sense to look at these such equations? So this immediately disproves what Brian Arthur said, that you could not write down equations that tell you exactly what he told us we could not do. I'm claiming that these kind of equations make sense. Why? Because you can nowadays with big data, you can measure what the networks look. You can see what the states of your individuals are, and you see the changes over time in these things. So all of these components here are known, and we can, maybe this F and G we don't know, but we can watch how the system is evolving. Big data is a glimpse, a movie of what these things are. So I think with big data, for the first time, these kind of systems become meaningful. 30 years ago or 20 years ago, you would kick me out of the room for this nonsense that I put here. So one observation that I think is interesting is all that you can store in a database is a multiplex network, something like this, which you can also draw like this. Okay? So it's maybe the reason why you see so much network, so much progress in network theory, because people are using every database, make a network out of it, analyze it, and publish it. Yes. Let's slowly converge to what I really wanted to say in this talk. We are interested in understanding human behavior a little bit better, and we found, more or less by chance, a Petri dish where we can do that under very controlled circumstances, and it's a computer game that we basically have. one day, a student showed up in my office and said he would like to do his PhD with me. So I asked him what kind of mathematics he likes, and he said, I hate mathematics. I said, okay, physics, what do you like there? And he said, no, I don't like physics. And then I asked him, what do you like? And he said, computer games. So I gave him mentally 2 more sentences, and then I would ask him to leave. And then he told me that he had programmed a massive multiplayer online game with a friend of his, which at that time was the biggest massive multiplayer online game in Europe, a factor of 10 smaller than Second Life. I don't know if you've heard about this. And then I asked him if he had the data of the log files of what's happening behind this game. And then he said, yes, we record everything. And so we had a deal. And now he has a PhD, and now he's at MIT, and we're all happy. So this is what, a massive multiplayer online game, which is played by almost 500,000 people. They are avatars. When you start the game, you're an avatar. You're associated with this. And this avatar lives sometime in the future. You get a spaceship. That's your car. And the first thing that you notice is that you have no money. So you have to start working somewhere for someone, or you become a little entrepreneur and harvest some space energy and bring it to a planet where you can sell it. And then you gain a little bit of money, which you can invest in all sorts of things. You can buy things, you can produce things. You meet people, you form groups, you form bigger groups, yet bigger groups. You form political parties, you form countries, you form states, you form city governments, you form all sorts of things. There's no rules in the game. You cannot be sexist, not racist. If you're one of these things, there's capital punishment on this. You're erased. But other than this, there is no rules. So there's no aim of the game. But still, at any point in time, 16,000 people are playing it. Good. So there's different lives or different motivations why people play this game. So there's an economic life. People produce things, they distribute things, they run an economy, they consume things, they spend the money they earn. Usually they spend it on prestigious objects. The first thing people do when they get a little bit of money is they buy a new spaceship. You can consume drugs, which delays time a little bit. So it's not a real physical world, but a little bit funny world. So there's an economic life, there's a social life. People talk with each other, they form groups. There's a news system. There is a jurisdictional system that's self-organized somehow. People tend to accumulate status. Whenever you give people the chance to collect some points somewhere, they will do it, and they will have a champion. And it's like in science, where we all do science nowadays to accumulate impact points. So it's the same in the game, that people collect war medals or expensive spaceships or whatever. There's also an exploratory life. Within the collection of 500,000 people, there's scientists who want to understand how this artificial world works. We have biologists, physicists, sociologists. Some of them are writing papers about the gravity of the planets that you find there. They're doing experiments, how much energy you consume when you pass with a spaceship by a planet. You can compute how the laws of gravity work there. It's different from the real or from first world. And there's biologists who are classifying all the monsters, etc., in a Linnaean scheme. And not only do you have these freaks, these scientists who are writing papers, they even have established a refereeing system. So they ask you to referee. The idea is that they're coming up with. So this is maybe your spaceship. You see a little bit, you're close to a planet. You can then zoom in, zoom in, zoom in, as we have seen today, always orders of magnitudes in, and then you can interact with other avatars. Yes. Okay, yeah. Humans, if you put them together, they immediately start to socialize, forming groups. Usually these groups are hierarchical. We have political parties in the game. We have people who started misusing infrastructure that you can build in the game, like satellites where you produce space beer. They transform these things into banks. So they're not shipping in the ingredients that you need for space beer and ship out the beer, but they ship in money and ship out money. So it's a bank. You're forming cartels. You're forming pirate groups. What is a pirate? A pirate is a person who steals something from another one, and you can do this in a little organized way. So you can rob big spaceships if you're organized, and then if such pirate groups occupy strategically important places in the game, you will immediately observe that people start organizing to get rid of these pirate groups. So they start forming a police force or a military, and they find people who like to be policemen, and it's a very rich surrounding. So this is a space monster. I don't know the Latin name of it. Yeah, so the cool thing about this is that we know everything about everyone, of every player. It's about 500,000 players who are playing now for almost 10 years. We know at every millisecond where everyone is, with who the person talks, what she or he produces, what they're shipping around, how they are, who is friend of who is aggressive to who destroys what from who is cooperating with whom. We know everything. And it's maybe the first time that we know that we have complete data on a human society. And now you say this is artificial, these are players, these are not humans. But I can tell you it's not bacteria, it's not rats, it's not guinea pigs, it's humans who are behind these avatars and who tightly associate with these, emotionally, with these avatars. So every time you think you have the best data in the world, you find someone who has better data. So we would like to offer this gentleman a PhD program in our group, but unfortunately no one really knows where he is except this lady. She of course sees him from her home. Yeah. Okay. So what do we do if we know everything? The first thing that we looked at is we can now look at the different levels of interactions humans interact on. So we can look at the communication network, we can look at the friendship network, we can look at the enemy network, we can look at the network of aggression that's forming, etc. So here, the green, so this is a subset of 100 players. We just picked out 100, and you see who is friend of whom. This is the green links. Here we have one guy who is extremely hated by many other people. So red links are enmity links. You can mark a person as being explicitly not your friend. So this is an enemy. So this guy did something bad, and people start hating him or her. And this is the communication network for the same set of people over, I don't know, a day or so, or a week. Yeah. As soon as you have these networks, you can compare them with real-world networks, like communication networks with cell phones, which we have. Can ask is this now really the real world? Is communication through a cell phone, is this real world, or is it also pretty artificial thing? So if you told this a person from the 17th century, he would maybe say it's also kind of second world. But we can compare the structure of these networks with real-world networks. And so to our surprise, these networks are practically the same. Okay? You can characterize networks by a set of characteristic numbers they have, maybe a dozen of numbers. Characterize a network like these pretty well. And these numbers are practically identical in the second world and the first world. What you can never do is to compare enmity networks with real-world data. Friendship data you have a lot. But enmity networks we don't have in the real world. Why? Because people don't, they're hesitant to write down the list of their enemies on paper. So I also would not list my enemies because of fear that they would see that I explicitly mark them as enemies. Yeah. We can see how basic network properties evolve over time. We see that in the first couple of 100 days of existence, the network kind of reaches a steady state. It's, of course, not really a static situation. Constantly, players are coming into the game. Constantly, players are leaving the game. But on average, we get more or less a steady state situation, telling us we can do some statistics. And one of the first things that we did is to test social or hypotheses from the social sciences, which are out there since the 70s. So we were testing the weak tie hypothesis, and triadic closure, for example. So what are these? So certain Mr. Mark Granovetter said that the degree of overlap of two individual friends, friendship networks varies directly with the strength of their tie to one another. Both of these things we can now measure. We can measure the overlap of a friendship network. It's a mathematical expression. It's not too complicated. And what it measures is the overlap between two friends, I and J, measures the percentage of friends that you have in common. Okay? The overlap of these two friends is 0 because none of their friends are friends of the others. And the overlap of these two friends, I and J, is 100% or 1 because all of their friends are also friends of themselves. So we can measure this overlap, and the strength of a tie we can measure by the number of exchanges of emails, for example, between them, or communication events between them. Then he goes on and says, no strong tie is a bridge. So what does that mean? A bridge is if two people who belong to a community, if they are holding these communities together. And this is, the weak tie hypothesis is that this is never a really strong tie. Okay? So there's reasons why he believed that. And you can easily quantify what the bridge is by the betweenness centrality. This is another network measure. And then we can do two things. We can plot what we observe in the communication networks, plot the overlap of people against the betweenness, and we can plot the overlap against the strength of links. And we see very clear curves, which more or less look like this. The betweenness is 1 over the overlap squared, and the strength is overlap to the 3rd power. Now we can combine these two equations and work out another equation, which tells you that the strength of a link is inversely proportional to the bridgeness. And this is exactly now doing what Granovetter said here. No strong tie is a bridge. It's exactly this. But what can we do? We can tell you what the formula is, how these two things are connected. Okay, and we call this our first social Kepler law. You know, in the Kepler laws, you have the size of the half-axis squared is equal to, I don't know now exactly, the times to the third power. So you have a power of 2 and a power of 3. It looks like a Kepler law. So this is now really a quantification of something that's really remarkable. Why is it remarkable? Because this is an individual quantity. The strength between Jan and me is just a function of both of us, but it relates to a global quantity, namely betweenness. I need to compute betweenness, I need the information from the whole system. So this tells us how the system feeds back on individual interactions on average. I think that's a really remarkable situation. And it has been confirmed, this kind of law, in the First World too. We're extremely happy. So we are waiting for more evidence for this coming in. Triadic closure is something not so abstract. It's these are all the triangles that you can build. There's 13 of them if you connect 3 points with an arrow. Okay, not more to say. Triadic closure is the statement, again by Granovetter, that a triangle that is missing one side, it has the tendency to become a triangle with 3 sides. Okay, so 6 means it was triangle number 6 here. That's this one. It has the tendency to turn into triangle number 13. We can now go and check how often is this happening in the friendship networks, in the enmity networks, in all of the networks, in communication networks. And I think this is for the communication networks. How often are we going from 6, this line, to 13, that row? Very often. And how often are we going to go the other direction? Not so often. Okay? And we can do that. We can measure the transition rates from every of these 13 triangles and get a transition matrix, which you would need if you want to simulate social processes. We'll come back to this. What we find is that triangles that are open, this is these triangles here, 1 to 6, are, for the friendship networks and the communication networks, are drastically underrepresented with respect to a random network. That's if you're below 0, there's less of these open triangles than you would expect from a random network, whereas the enmity networks are overrepresented. Okay, so this is a clear indication that Triadic, no, it's not clear. The closed triangles are here, and we see that for the friendship networks, these are overrepresented. So more evidence that Triadic closure is happening, but only in the friendship networks, not in the enmity networks. The enmity networks, we have exactly the reverse effect. Now, if we find out this, if we see Triadic closure is happening, to what extent is it happening in a social system? For this, we designed an extremely simple model. It's like this. At time t, we have this situation. We have these 4 nodes. 2 of them are connected. 3 of them are connected in this way. And now with probability, with a certain probability, we close the triangle. And with the opposite probability, we don't close the triangle, but establish another link. It's an extremely simple model. And all that we do is to create new links, new nodes. At a certain rate, we destroy nodes. At a certain rate, we destroy links at a certain rate, and we introduce links at a certain rate. So we have 4 parameters. That's it. And we can all measure these parameters from the game. And then with those four parameters, we put these into this model, and then we can reproduce pretty well not nine numbers that characterize social networks, but we can reproduce 9 functions that represent the actual measured social networks there. This is also something extremely remarkable. So these are the 9 experimentally observed network properties. I don't go into them. The red dots are the data, and the blue dots are the model. So you see that for many situations, except maybe those 2, we can reproduce the social networks completely, the structure of social networks completely by this triadic closure. So this means that the Homo sapiens is an animal that does nothing else but trying to close links into triangles. This is something that drives the construction of our social networks. Okay, since we have these networks at the different levels, we can look at the degree distributions of networks. A degree distribution of a network is a property of a network. That's one of the simplest properties that you can do with networks. The degree distribution is the probability that if you grab into a network, pull out one node, the degree distribution is the probability that that node that you pulled out has exactly k links. Okay, so if we put the number of links here, this is the probability that if you blindly reach into a network, pull it out, that it has exactly 10 or 100 or 1,000 links attached to it. If these curves bend, you know that there's a large random component in networks. These are random graphs to a large extent. So for friendships, communications, and trade, we see that they're predominantly random graphs. Whereas if we look at negative interactions like hating each other or attacking each other or putting head money on each other, these are all not nice actions. And we see that we get straight lines here, which are indications for scale-free networks. This is this type of networks where there's so much fuss about in the last 15 years because there's ways to understand how they grow. Okay, so in the type of networks we see, or from looking at very simple measures for networks, we see that different interactions have very different network structures. Okay. You can ask the question, how are 2 levels of networks related to each other? How does communication affect trade, for example? And this is everything but easy to do. It's an open question of how to measure the interaction of 2 networks. We are trying a little bit, and we are understanding a little bit, but it's all work in progress. What we find, very remarkably, that friends talk a lot with each other. So this is maybe a thing that you would have guessed, and we find that in our analysis. What you would not have guessed is that if people attack each other and are really aggressive with each other, they also talk to each other a lot. So aggression is not anonymous, and we can measure the degree of how not anonymous this is. There is an even older social concept of social stability, or not a social concept, a concept from social science, dates back to the 30s, certain Mr. Haider came up with the notion of social balance. He says if you have a triangle and if a plus sign means that these two nodes like each other, these are friends, 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 this should be, this is balanced. This is a stable situation, should be reflected by being overrepresented in the network. This, in contrast, is the opposite. This is unstable. Plus, plus, minus is unstable. So what he said, whenever you multiply all these plus and minus signs in a circle, if the result is positive, it's balanced. If it's negative, like here, plus, negative, plus is negative, is unbalanced. Same is true here. This is balanced, and this is unbalanced. Now we can, again, check if that prediction is true and to what extent it's true. What we find is that not only are these structures, the balanced structures, overrepresented in networks, but they are overrepresented by significance, which is mind-blowing. This is 71 standard deviations of significance. I remind you that for the Higgs boson to exist, you need 5 standard deviations. So this is high-precision social science. So here we have even 100 standard deviations for the unbalanced situation. So this is really underrepresented. You don't find these structures in social networks, in positive, in friendship and enmity networks. And yeah, this is overrepresented. And this is only significant at the Higgs standard. Okay. Let's look at societies at a different angle. We're talking still about these multiplex networks that evolve over time. But we look at it from a different angle. What am I? I am a protein synthesizing object that is performing tasks over the day. The first thing is I get up, I brush my teeth, I drink a coffee, I talk with my girlfriend, I go to work, I quarrel with this guy. And the last thing is I brush my teeth and go to bed. And then I repeat more or less the same things most of the days. And there's maybe a couple of 100 actions that I do typically. Or let there be a couple of thousand if you really want to be granular. Or even 10,000. The computer will not care how many actions you can do. In the game, we look at around a dozen of actions that you can do. Every action is a letter. So C is for communication, A is for attack, B is for putting head money on someone, T is for trading, etc. And we can come up with a code for every player that looks like this. It looks like a genome. But it has a little bit more letters. The genome only has 4 or 20, depends on how you look at it. And almost every action is directed toward someone. So we have little arrows here, meaning that this player attacked at this point in time this player. Okay? And here this player traded with this guy. So it's the behavioral code, and every code of you is interacting with the code of all the others. It's exactly the same information, just now looking at the more temporal angle. And yeah, a little bit nonsensical. What we can immediately do is to ask questions like this. What is the probability that if I did this action now, what is the probability that I do any other given action at the next time step? This is captured, for example, in this transition matrix again. So this means that at time t, if I communicate, the probability that I will receive a communication action from someone else, this is the little r for received, is pretty high. Okay, if I talk to someone, the probability is high that the guy talks back to me. And the probability that if I talk to someone now, that I attack someone else at the next time step is extremely low. Okay, I can read every possible combination off. And from this, I can make statements like this, that on average, even though you can be a very bad person in the game, typically you're not a bad person. 97% of all the actions that you do in the game are positive, are not damaging others. So the probability of a negative action following a positive action is 3%. So only 3% of the actions are negative. But if you receive from someone a negative action, you're attacked or you're accused of something, or someone steals something from you, the probability that you will act out a negative action in the next time step jumps by a factor of up to 10. Okay? This means you have a completely overproportional reaction to aggression. The Homo sapiens is an animal that, in principle, lives in peace. If you attack it and challenge it a little bit, it completely overreacts and gets really aggressive. So I've learned that in every talk you have to quote a big thinker. So here's my tribute to one of the brilliant minds in the Western world. So if we have a sequence of actions here, communication, attack, blah, 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 we assign a plus or a minus to the plus to positive actions, minus to negative actions. And if it's a plus, we draw a line upward. If it's negative, we draw it downward. So we are seeing a line for every person. Yeah? If the line is always going up, the person is a good person. If the line is always going down, it's a very bad person. So how do people look? This is, I think, 10,000 players. 99% of all players are in this upper front. People, even if they can do bad things, they can kill each other, they can rob each other, they don't. They self-organize to be pacifist to a large extent. Those people who are bad tend to live not so long. So either they are hunted down, or they just lose the fun and don't get anything out of it anymore if they just are confronted with negative reactions from others. So there's this self-cleaning effect, this structuring effect toward organization of a cooperative society. This is what we would not have expected, this degree of cooperation in a game like this, which is where you have all the equipment to do bad things to others. You have these space guns and shields and all. If you look at these sequences, I told you it looks like DNA, like genome sequences. You can use the same methods for it. You can use all the math that has been developed for analyzing this, and sure enough, you find a Zipf law in the behavioral code, meaning that there is scaling laws, which might be understood with some tools that we have in complexity science. And we think we know why this Zipf law is emerging here. We can look at gender differences. When you start the game, you have to pick a sex, a gender. So you can basically choose from hundreds and I think even thousands of different icons. Do I have, yeah, here it's better. So you can choose a character. You can, it's always a male and a female version. So if you pick this, you have to find out really what is female about this one. And I think it's the eyes, or I don't know. But you have to pick one. So the states of the nodes is male, or male is blue, yeah, and red is female. So we just look at how are females doing economically. Yes, they're a little bit richer. They're more active in producing things. Females are, they attract positive behavior. So in groups around females, there's much less aggression. And females like to be around with other females, and males like to be around with females. So we're looking at biology here. It's really crazy that we can do biology in this computer game. Now, let's look at networks. This is, sorry for the quality of this plot. This is the difference of communication partners. It's the difference, I say it for those who understand what networks are. This is the difference of the degree of males minus females. So if males have more, and this is for friendships, friendship networks, for communication networks, PM stands for private message, trade networks, enmity networks, attack networks, and bounty networks. So what we see here is that females have, on average, 5 more communication partners. Okay, this is a lot, given that the average of communication partners that every one of us more or less has is 10. So the people that we are calling on our cell phones on average is, I think, 7. The clustering, the difference of clustering, what is clustering? Clustering is in how many triangles are you embedded in your local social network. If you're embedded in lots of triangles, generally this is a much more stable situation than if you're not embedded in triangles. Females tend to be much, much more clustered. Females are producing social networks where really the friend of the friend are friends. Males don't show that quality. The networks of males are much larger, extending over much larger space, but they're much less stable. So they look much more fuzzy. And female networks look more compact. Again, it's biology, I think. Females keep the group together, and males are having fast communication networks. That's what the effect of having a fuzzy network is, that you get information flows fast, but these networks are unstable. That's the cost for it. Okay. Females have much, much less communication. What I show here is the difference in nearest neighbor degree. So this is the average number of friends that my friends have. Okay. Males look that they are connected to males who have lots of other friends. Females don't. Very different way of building networks. And reciprocity, what is reciprocity? That's if I establish a friendship link to you, will you also establish a friendship link to me? The proportion of how this is reciprocated is generally larger for women. Also, nice cliche that one can quantify here. Yes, I think I told you all of this. Here's again our degree distributions. Now for males, blue, and females in red. You don't see much here because this is a logarithmic scale. But if we plot the difference of blue minus red, we get these plots here. And these we can, again, interpret very nicely. We can see how different the the two species, male and female, really are. For friendships, so again, if this number is negative, it's dominated by females. If it's positive, it's the males that dominate that number. For friendships, males and females have more or less equal numbers of friendships. This is the K here is the number of friends that you have. If you look at those people who have really many friends, from 10 to 100, it's the females who have those. Okay, so all the rankings, numbers of friendships are dominated by females. In communication, females talk more, except for the super communicators, these are males. In trading, females are a little bit more dominant than males, and there's no dependence of number of trading partners, not much. For the negative ties, friendship, the enmity networks, males dominate the enmity network, so men have more enemies than females, up to a certain number. And if this tells you that if some people are hated, really hated, then they are hated through women. Attacks is a purely male thing, whereas head money and bounties is a pure female thing. So it's a completely different way of handling aggression. So it's again maybe handling aggression and managing conflict. Maybe there's biology behind this too. We can do other experiments. So trying to prove Brian Arthur wrong. This is the decay functions of radioactive material. And I'm showing you very similar curves, semi-log plot. These are response times to actions of players. So what do we measure? A male makes a suggestion, you're my friend. Establishes this link. Then we measure the time. How long does it take until I get a positive response to that action? And then we plot the histogram of this, and we find these decay curves. And we see fantastic differences, again, in decay times for males and females, and all the possibilities. So if a male tells another male, you're my friend, the male very often ignores that. I don't care if he's my friend or not. If a female sends a message to another female, I'm your friend, then the response is much, much faster, an order of magnitude faster. Yes, I'm also your friend. If a male sends an aggression, or if a male marks someone else as an enemy, the response is extremely fast. Yes, I also hate you. And if a female marks another female as an enemy, it's ignored. So again, different management of aggression. Yes, this is what these plots tell us. So it's really different plots. This is again a logarithmic scale, so huge differences. Yes, and we can look at gender differences of network interactions. Dirty business, hard to interpret, not clear if it really gives us a message. So I'll skip over it. Yeah. People in the game have incomes through their economic activities, and some are rich, some are poor. So here I show you the dots. Look at the dots first. This is the wealth distribution of the English, is the circles. So we see this, I don't know what this function really is, but this is the income, the wealth distribution of England, of the UK. The triangles is a rescaled a little bit rescaled income distribution or wealth distribution for the Swedes. And the blue curve is the wealth distribution of the PARDUS game. So again, you see it's pretty real world. And here we can now, we had a project of trying to understand where does the difference of wealth originate. So is it a social thing or is it not? So we can compute the Gini index. It's an index that tells you how wealth is distributed in a nation. If it's, I think if it's one person owns everything, the rest owns nothing. If it's zero, everyone owns the same amount. And we look at the Gini coefficient. No, that's wrong. Now we can look at the average wealth in the game, and we look at the Gini coefficient. So at the start, the system is totally egalitarian, and then after a couple of 100 days, after a year more or less, we are reaching more or less stationary states. Gini coefficients are a little bit higher than in the real world, fluctuating around 0.6. And here we did an experiment. And the experiment was that at Christmas Day 2008, I think, there was a charity action proposed. Players in the game could donate some of their wealth to give a Christmas gift to the poor. Many people donated, and the proceeds of this action were distributed to poor players, which reduced in a single day the Gini index by a massive amount. And we would say, okay, what would we expect? That it stays down there for a while and maybe goes up slowly again, but we see that the Gini index goes up exponentially fast. Okay, so it's not a matter of luck or not, of being rich or not. It's something that's encoded somehow. Where is it encoded? It's maybe encoded in the social networks. That's what we then looked for. Where in these multiplex networks do I have to sit to be rich? The space, the parameter space of saying where am I sitting in these multiplex networks is extremely high. The dimensionality of this is extremely high. So the dimensions are the average degree in the trading network, the average degree in the friendship network, the nearest neighbor degree in this network, all of these network measures in all of the different things. So it's very high dimensional space. We found a couple of interesting situations that rich people tend to cluster if they have many trading partners. So number of trading partners is in this direction, the degree of the undirected degree for the trading. This is not so surprising. If you trade with many people, you're rich, okay? What's unsurprising is that there's an optimum of the average number of trading partners your friends have. Okay, so it's a next order effect. If your friends have on average too many other friends or trading partners, you're not rich. If they have too few, you're not rich, but there's an optimum. This happens in many, many cases that we find places in parameter space where rich really cluster. Okay, and we wrote a whole paper on it, on trying to make sense out of this. So whether you're rich or not depends on many, many, many factors, but basically it's a position in your social space, which we can quantify for the first time. What we did here is we looked at the question if, as I told you, people are forming groups, and there's a formal way of forming a group, like there's a formal way of forming an association. You have a boss and a finance guy, and you specify all these people, and people love this. There's hundreds and hundreds of such groups, and we can measure how big these groups are. And does group size matter in terms of wealth? So what we see is this is group size here. This is average wealth. And we see, okay, there's basically no effect of group size on wealth. This is the Dunbar number. This is the maximum group size that we see. This is this magic 150. So we again see some biology. So the message here is if people are totally asocial, if they're not part of any group, they're poor. As soon as they form small groups of around 5, okay, they're not so poor anymore, but from 10 on, the group size does not matter. So it matters if you're social or asocial, but then the group is not so important anymore. So a last thing, how am I doing in time? Huh? So we have a little more time, okay. In physics, what is a force? A force is something where you have two objects and a gauge boson is exchanged between these two things. So in electrodynamics, this gauge boson is a virtual photon. In the strong interaction, between quarks, gluons are exchanged, and between other particles, it's the W bosons and all of these things. So here you have two of these things, protons, a proton and an electron, and they are exchanging virtual photons, and this keeps the proton and the electron together. If we have humans, they also exchange things all the time. They, all the social networks that we discussed are based on exchanges. If we communicate, we exchange emails. If we hate each other, we exchange bullets. So it's always, or if we like each other, then we exchange gifts. And the question is, does this exert a force, this exchange of things, does it bring humans together? Do they accelerate when they exchange many of these things? Or do they repel each other if they exchange things? So we're following the question of Newton again. So again, proving Brian Arthur wrong. No, not proving him wrong. What we have in the game is a space, a map. So this is different cities. You can zoom into those, and then you will see that there's planets and there's clusters of satellites around these planets. You can zoom in, zoom in, zoom in. This is the coarsest level that you can look at. This is the universe. The links here is wormholes. You can go from one part of the universe to another through a wormhole. But basically, this is just a street map, a two-dimensional universe. And we are asking, are people who exchange messages from here to here, will they be likely to move closer to each other, or will they repel each other? And what we are, since we have millions and millions and millions of these observations, we can really derive interaction potentials, as you can do for proton and electron. And these look pretty harmonic if you're a physicist, except the one for attacks is this one, where you see a clear minimum. So if you think of how an attack is happening, you first have to approach your victim, and then you have to run away fast, that he doesn't reach you. So this gives a little bit of a funny kind of potential. So it's not a harmonic potential, but it's dipping here below 0. And from this you can, if you have the potential, this is the potential here. If you take the derivative, you get the force between people. So this is our Newtonian approach to complex systems. No, it was a fun project. We are not giving much meaning to it, but yeah. It's an introduction to my last slide. So can we make a quantitative predictive experimental science out of social science? I would not be convinced, but we can do cool things with these big data sets. That's what I would like to get across. Yeah. What do we do if we have complete information? The limit is our fantasy. It's not the data anymore. It's not the computer capacity anymore. It's our imagination. It's our creativity of how to solve the complexity barrier. We have a lab situation. People that we are observing are not aware that we are observing them. They are legally aware because they tick off that it's okay that we use their data for scientific experiments. And people in the game, every time we publish something, it's discussed in the game. And yeah, sometimes favorably, sometimes not. Yes. Okay. I think with this, I will end. Thank you.
Stefan, thank you very much indeed for a fascinating paper. And I say that as someone who is instinctively, as a historian, very suspicious of this sort of model.
Good.
I find that really fascinating. I've got so many questions, but I'm just going to go for two, if I may. One is, I am fascinated by network theory and how it may play out in relation to the idea I described yesterday of collective learning. And I've not gone, I'm not a mathematician, I've not gone that deeply into it, but one of the possible correlations that fascinates me is measures of connectedness are one of the most basic, you know, the measures that give you hubs or isolated individuals. And I very often wonder whether there's a strong correlation in human history between connectedness and power and wealth. Mm-hmm. So I was looking for that, and I may have missed it in your description. So that's one question. The second is do you know Steven Pinker's book, The Better Angels of Our Nature? Oh. I think it's a wonderful book. It's generated a lot of criticism, but his basic argument is that levels of interpersonal violence have plummeted in the last 200 years.
I know that slide.
Before 200 years ago, you know, levels of personal violence have been high for thousands of years, maybe back into the Paleolithic. So something really profound has happened in human relations. And that raises for me the question, your avatars are all 21st century people. So, and I'm thinking of this particularly in relation to those statistics that seem to show how good most of them are. And I'm wondering if there's a sampling bias here. In other words, you ought to be getting some players from the Paleolithic in your game. But that's actually a serious question. So thank you very much.
Okay, with respect to your first question, we tried to do exactly this with this kind of plots. We look at not power, but wealth as a function of where you are in these networks. And this is now, these things here, these axes here, are how connected are you in this and that network. So this, if there's a K, that's the connectedness of nodes. It's not always a K, but it's all, okay, here's always a K. So this is exactly what we're trying to find. And we see it's a multifactorial, wealth is a multifactorial thing. We have historian friends who are looking at multiplex networks of medieval data. So they know every letter that was sent around in a couple of hundred years. They know who married whom. They know who attacked whom. They know how the thing got resolved. They knew who was the vassal of who so this is maybe again a dozen of different networks, not a dozen, maybe 5, and yeah, they're not. It's silly to think of predicting historical events, but they tried to see from networks who was how powerful and how many people could he motivate to join him into a battle and things like this. So there is a couple of groups in the world who are doing this with history data. And yes, would be interesting to get a couple of guys from the Neolithic to to play it and see if they would play it in a much more aggressive way. We have 3 universes running in parallel. So we have 3 different histories. So there's, it's not one, it's one type of game, but it has 3 copies of it. And 2 are free, and for the third one, you have to pay. Nothing is different in the game where you have to pay, except that the colors are a little bit nicer, maybe, and it's differences of this kind. And I think you pay $5 per month in this other game, and the aggression level in the universe where people pay is much less. Much less. So they are much more careful in doing bad things to others than in the other game. They're more concerned about their lives. So this is maybe an answer that we can give to your question within this data set.
I have a question. Do you know the demographics of the players?
Yes,
and
we do.
Could you say a little bit more? And in particular, how long do they play? How long do they play the
Stay
game?
in the game.
And average hours per day or per week?
Yes, okay. Yeah. So most of the players are American, then followed by Germans, Japanese. There's an over-proportional group of Austrians because it was publicized there a lot in the media, and etc. But some players, or many players, in fact, stay for a very long time. Once they have hit, I don't know, a 3-week barrier. So if you're there, most players come, check it out, think, it's kind of boring, and then they never come back. But if you played it for 3 weeks, then the probability that you will play it for another 3 years is very high. So it's a big fraction of very constant players. You can only play it about 15 minutes per day. Every day you get action points, and you can use these up, and then you have to go to sleep and wait for 24 hours again. This is to keep out those players who can spend 22 hours a day in the game, and this would dominate everything. So we have this How old? No, there's no age limit. I think it's around 25. The game is aiming. The game is aging. Since it's not, it's 10 years old, so it's not so attractive for new players anymore because the graphics is totally out of fashion. And around 25 is the average age.
This is going to seem maybe very obvious, but the only other comparable data set I can think of are the primate studies, the Stanford or the von Schaik with the Arnhem Zoo, or the Stanford primate colony, the macaques and chimpanzees, where they're watching, and they're really looking at they do very similar calculations of friendship and enmity and so forth, and it's exact data. Mm-hmm. There's also, of course, data in the wild, which is also very, every 15 minutes, what each animal is doing. So I wonder if you tried any comparisons.
No, not yet, but I'm aware of this, and with Simon Tadeo, we decided that we should do something in that direction, but we never did.
So we just have two more questions because time is getting here. So maybe this gentleman first, followed by that. And
thank you. I don't know whether you're aware of Vernon Smith, the Nobel Prize winner, trying to evolve exchange networks. And he first of all had students play in a world where he kind of knew what the economically efficient solution would be. And what he did monitor was they weren't allowed to communicate via messages. So he knew exactly all the words they used. Is there words in your data which could give us some idea of the cognitive dimension, not just the behavior?
We're for good reason, not looking at the content of the messages that are exchanged. We could, but I think it would cause a revolution in the game. If we change a color of the email system in the game, or the communication system, or in anything else, there is all sorts of conspiracy theories that someone is changing their world, and we have up to 5,000 people leaving a day if a major change happens.
We are all controlled by the circadian clock, the 24-hour rhythm. So have you looked at exchanges as a function of time of day, whether we are more aggressive or friendly?
So the day is very short?
No, but you have your data when they play. So,
Yes.
So it's a circadian effect, a 24-hour effect.
Since it spread so much across the globe,
but you know where they are. And
we know where they are. So in total, the effect washes out. But if we bring everyone to his eigen time, or to the time when the person is logged on during the day, then we observe typical frequency patterns that are comparable with those observed in the real world. So when do people call their friends? It's in the morning, it's in the evening, or late evening. During working hours, you call them not so often. And we see similar double peaks for communication, etc. also there.
But not with respect to content, aggression or positive exchanges. That's the question, actually.
Okay. If that's different across the day, we have not looked at this systematically.
okay, thank you for your question. So if you have further question, please feel free to talk to Professor Thurner at the coffee break. So before I close the session, I'd like to present a token of appreciation to Professor Thurner
Thank you. Thanks.
for the very interesting talk.
Very much.